All right, in the last video, I tried to convince you of two things. The first is that KD is a really important thing for us to measure when looking at how receptors and ligands come together. This is going to be super important for anybody who's a doctor because you're going to be looking at studies that are going to be talking about KD of drugs binding to targets and things like that. It's also going to be really important for people who are out there designing drugs because KD is the predominant way we ensure that inhibitors and things like that are binding really tightly to their targets. The book does a good job with this area, so if you need a backup, take a look at that and make sure you've got the theory behind it. The second thing I wanted to convince you of is the way we measure KD with receptors and ligands is to mix them together at varying ligand concentrations. And we'd measure fractional occupancy of the receptor. We'd plot it out and we get a sigmoidal curve. Now remember what I said before, that sigmoidal curve does not mean what it normally means, which is cooperative binding. In this case, it means we have a hidden hyperbola. It's simply a mathematical little trick. By plotting it as log of ligand concentration, we stretch that hyperbola out, and this is the kind of thing you're going to see in all sorts of studies that you'll see in the future. So those are the two things where we're at. So why can't we just be done with it? The answer is because while this is a very effective way to measure KD, it's kind of hard to do. And the reason for that is because detection of binding, which is what we need on the y-axis, requires separation of bound and free receptor. And that, it turns out, is not easy to do. We also need very high sensitivity. And that's not very easy to do either. There's a couple of analytical techniques that we use predominantly for this type of experiment. We can use UV spectroscopy or even visible spectroscopy on occasion. Fluorescence is much better. This is more sensitive. Lots of techniques use fluorescence now. It's pretty sensitive, but largely it's not good enough. And if you really want to do these studies well for really tight binding molecules, you got to use a technique that's extremely sensitive, and that's almost always going to be radioactivity. So we're going to look at different types of isotopes that are used regularly for these types of things. I've used all of these in my career. And what I can tell you is that these are the common ones. P32 or 32P we would put down, that's phosphorus, and its radionuclide is going to be used for anywhere we have phosphates, and that's going to be nucleotides, DNA, and RNA. So very highly used, especially for kinase reactions, phosphatase reactions where you have ATP involvement. Fats and sugars, we're going to use almost always C14. That's a real downer because that's got a half-life of 5,000 years, so it's hard to get rid of that stuff. But fats and sugars don't really have anything else that can be used except for tritium, which we'll get to in a minute. Tritium, anything, is going to have protons on it. You can swap out tritium, but that's also a real long half-life. We're going to see S35, that is sulfur 35 for proteins, and we can also use I-125 for proteins. I-125 can go on to tyrosine fairly easily. So all of these things are used constantly in the pharmacology industry, and this is how you measure these things. That's how you get fractional occupancy. So it's a pain, it's expensive, there's a lot of bookkeeping. I wouldn't say it's particularly unsafe, although you just have to be careful with it and shield yourself. But it's a lot of rigmarole. You have to suit up and get gloves on. It's not a lot of fun to do these experiments. And plus, we don't want to have to take every molecule we synthesize as a potential drug and make it radioactive. That's a real nightmare of work. So we've come up with different ways to handle this. And in particular, we're going to use competitive binding of hot and cold ligands. So let's move on to the next page, page 320, and see how we can take this to the next level. We're going to talk about hot ligands and cold ligands. Hot simply means radioactive, and fortunately you can purchase a lot of things that are already radioactive. So let's say you want to make a molecule that you think is going to bind to the insulin receptor. Well, you can buy hot S35 labeled insulin, and you don't have to synthesize it yourself. Cold ligands are going to be non-radioactive inhibitors. Let's say you're working in an organic synthetic medicinal chemistry lab and you've made 35 compounds off of a lead compound. You don't want to make them all radioactive. You just want to make them all non-radioactive. They're easier to synthesize. You don't have to have record keeping of swipe tests and all this stuff and shielding. So you can go ahead and do your chemistry under non-radioactive conditions, and then you have something to compete with the hot ligand. How does this work? Well, we're going to do a competition assay. It's really easy, actually. In the assay, we are going to have receptor, just like we did on the previous page. We're going to have a hot ligand, such as radioactive insulin, and you're going to put these together in a constant combination. You're going to usually use the hot ligand at a ligand concentration that'll give you 90-95% saturation from the previous experiment that we did. And then you're going to add in increasing concentrations of the inhibitor, that is the cold ligand. So let's take you through this. We are going to do fractional occupancy. We can measure that because we got a hot ligand in there that we can separate out and measure. We're going to do that as from 0 to 1.0, just like we did before, with a 50% mark right there. Now, this time, instead of increasing ligand concentration, we're going to do increasing inhibitor concentration. And again, that is the cold ligand, the thing that is non-radioactive. So this time, instead of starting at 0, 0, we're actually going to start way up at the top. Why is that? Because if we've got a certain amount of hot ligand and receptor bound to it and no inhibitor, then you're going to get good binding. And that's full binding at 0 inhibitor. Now, by the way, we're going to do this as a log inhibitor concentration as well, just like we did log ligand on the previous page. Let's say we then put in some inhibitor and we keep adding more and more inhibitor, but let's say this inhibitor doesn't bind at all. It's a terrible binder. It's a not good drug candidate. What's going to happen? Just think about that a little bit for a second. What would the curve look like? Well, if the inhibitor doesn't bind, it can't compete. And so we would see right across the top like that. So let's make a note of that. No inhibitor binding. Great. Let's take a different color and let's consider something that has relatively weak binding as an inhibitor. Okay, we're going to start with 0 of that inhibitor. You put in some and maybe it goes down just a tiny bit more, and eventually you get enough of it in there, it starts competing and swamping out the other hot ligand. So what happens is you actually see the hot ligand or fractional occupancy go down because the cold ligand is competing with it and preventing it from binding. So this would be let's say call this a weak binder or weak binding inhibitor. And lastly, we could come in with a very strong tight binder, and what that's going to do is very little of that weak binder, that tight binder, is going to be needed to compete. Because it's so good at binding, you get that stuff to come off a lot quicker at a lower concentration of inhibitor competition. Okay, well, how does this help us? We want to know how tight the inhibitor is binding. And the way we do that is we go again to the 50% mark. We're going to go from 0.5, we're going to go over to our curves and drop them down. This time, though, the measure right here is going to be the IC50. That's the IC50 for the blue tight binder. This is the IC50 for the green weak binder. The red one that doesn't bind at all doesn't have an IC50. Well, what's IC50? IC50 is the inhibitor concentration that gives 50% inhibition of hot ligand binding. Now, our goal is not to measure IC50 because that's not true constant. It's not something you can look up. It's only a relative value. Our goal is to determine how tight does the actual inhibitor bind. We want to know, is it going to be a good drug candidate, for instance. Before I go and tell you how to do that, I want to point out something. This is actually not the log, or rather the IC50 right here. It's actually the log of IC50. I just want to be technically careful about that because when we read that off that scale, it's in a logarithmic form. You've got to take the inverse log, that is the 10 to the x version, to get the IC50. So be careful about that as we work on that. When I showed you on the previous page, maybe I'm going to even go back there for a quick second. This is not the KD here. This is the log of KD. I want to be clean about that because the math will be different if you treat that as the KD. It's actually the log of KD. Okay, let's get back to this. We know the IC50 now from our graph by drawing down from the 50% saturation level. What does the IC50 do for us? Well, we don't want the IC50, like I said. We want what is the KI, K subscript I. And this is going to be the same as the KD for inhibitor. In other words, it is the equilibrium dissociation affinity constant for inhibitor, whatever inhibitor you're using as a cold ligand. This is the constant that we measure to tell how tight that inhibitor binds. We want it to be really low, just like we said for regular KDs. Low equals tight. And for any drug you're trying to design, you want it to be really tight. How do we get this determined? It turns out to be very simple. We use what's called the Chang-Prusov equation, very famous thing in pharmacology. It shows up in a lot of things. It's actually used in enzyme inhibitor kinetics. You might recognize it in some form there. And what we want to do is measure the Ki right there. That is the Kd for the inhibitor, meaning how tight that thing binds. We take the IC50 and we plug that into the numerator. We divide that by this term, 1 plus ligand concentration. Now this is, we got to be careful here. This is the hot ligand. Remember I said in this experiment we use a constant amount of receptor and a constant amount of the hot ligand. Whatever that concentration we used, we know because we put it in there. We put that in as the hot ligand concentration. We also then have to plug in the Kd for the hot ligand. So in our example we used before, if we were doing trying to design something for the insulin receptor, we'd use a particular concentration of hot insulin. We know the Kd. We already measured that on the previous page from the direct binding assay. And we then measure our competitor, get IC50 in there, and you can calculate out with simple algebra what the Ki is. One last thing here. Ki is, let me make a note of this because it's important for units issues. Ki, like Kd, like Ks, like whatever, Ki is equal to the concentration of the inhibitor that gives 50% saturation. So if I were to just interact that drug without any competitor around and interact it with the receptor, whatever 50%, whatever inhibitor concentration gives me 50%, that is what the Ki is. What that tells you, and this is really important, is that this has units that are related to concentration. You better end up with something like micromolar, nanomolar, femtomolar, molar, whatever. It's almost always going to be one of those molars, and that's because it is a concentration of inhibitor that gives 50% saturation. Okay, I'm not too worried about this, even though this is very dense stuff, because you're going to practice this out on homework, and it's going to make a lot more sense when you do that. So we'll leave it till then. Thanks for listening in. 2 long videos today, but just 2 videos, so we're all set for this day's dose.